Ready? All right then. Let's first talk about what the heck this word means. Polynomial. I'm sure you've heard it before. What is a polynomial? The word poly means many. Polynomial then does mean an expression with many terms. It doesn't have to have a lot of terms. Something with one term is still considered a polynomial. It's a special type of polynomial called a monomial, but polynomial function in general form. Will look something like this. They use p of x instead of f of x. They could use any letter, but they use p of x for polynomial. Yeah. That's a subscript. It's a little n. It's an n, yeah. Now, the reason they write it in this general form is to show that the exponents are in decreasing order. So the largest exponent comes at the front of the polynomial, and then the exponents need to decrease until at the very end you get a term with no variable. Remember what those are called? A term that has no variable? Constant. So the constants that are at the end. This term right here, a sub 1 times x to the first power, that's a linear term. And then it just increases up until the highest exponent of the polynomial. Okay. A couple of vocab words here. The term at the front is called the leading term. The coefficient is called the leading coefficient. And then there's something that we refer to called the degree of the polynomial. The degree of the polynomial is the highest exponent. So when you're asked to consider the degree of a polynomial, what do you look for? The highest exponent. And if it's written in descending order like it should be, it's the degree of the first term. And the degree makes a big difference later on when we graph these. You have to consider the degree of the function in order to have an accurate representation of the graph. Now, anything with a lot of terms doesn't necessarily mean it's a polynomial. There are certain characteristics so just because an equation has a bunch of terms doesn't necessarily make it a polynomial. First, all exponents are positive all of the exponents must be positive integers. If you have any rational exponents, meaning fractions, or if you have any negative exponents, it's not considered a polynomial. Second, there are no variables in denominators of fractions. So you can still have fractions as coefficients of variables, but you can't have any variables in the denominator of fractions. Third thing refers to its graph. Graphs are what are called smooth. Smooth and continuous. Their graphs must be smooth and continuous. The characteristic smooth means no corners. We've seen a graph that has a corner. What is it? What am I thinking of? Absolute value. That graph comes down to a point. That's not considered a polynomial function because its graph is not smooth. Continuous means if you were to put your pencil on the graph and just trace along the graph, you wouldn't have to lift up your pencil at all. You could just trace along the entire graph throughout its entire domain. So last test we just took, what's an example of a test? The piecewise. Those are not continuous because you trace along part of it and then you have to lift up your pencil and go to the other part. Those are not continuous. So continuous means no breaks or gaps. No breaks, no gaps. Fourth thing, this is kind of nice actually, the fourth thing about polynomials, and this is true of any polynomial of any degree, domain, is all real numbers. For any polynomial of any degree. So let's go into the first topic, zeros. Zeros of polynomials. Did you need a note, Cole? Okay. Write this down. Zeros. Zeros are nothing more than x-intercepts. You need to remember that connection. Zeros, x-intercepts, they're the same thing. Which are also the same thing as this. Keep writing. Zeros are x-intercepts, which are also solutions to the equation p of x is equal to 0. The reason so much emphasis is placed on finding the zeros is because eventually we're going to graph these polynomials. So if you can find the zeros, you've also found x-intercepts, which will make your graph much more accurate. Okay? And the other reason we're finding zeros is because it helps you practice solving equations, which is really important. So let's do example 1. I'm sure you have seen something like this. This is more of a simple one. You probably learned last year in Algebra 2. Find the zeros. Start with an easy one here. P of x equals x squared minus x minus 6. Now, how do we find the zeros? Take a look at this. Zeros are the same thing as what? Solutions to the equation p of x equals 0. So to find zeros of a polynomial, we need to set the polynomial equal to 0 and solve the equation. So we say 0 is equal to x squared minus x minus 6. You set the equation equal to 0. That's why they're called zeros, is because they're the x values that make the polynomial equal 0. You know how to solve this. I know you do. It's in there. Somebody said it. Factor. We can't actually do the square root method here because of this linear term in the middle. We have to solve this one by factoring. If it doesn't factor, by the way, what's the only other way you can find zeros if it doesn't factor? The quadratic formula. This one does factor. Luckily for us, it factors into x minus 3 and x plus 2. Which means the zeros will be what? X equals 3. X equals negative 2. So those are the zeros. So in terms of the graph, what are they? Those are the solutions to the equation, but graphically, what do those represent? Those are the x-intercepts. You have to have the x-intercepts in order to graph. Now here's something you need to consider. Answer this question. What was the degree of that polynomial we started with? Degree 2? If we look at the highest exponent, it's degree 2. Second degree. How many zeros were there of the polynomial? There were 2. Okay. What connection are we making here? What degree was this? Second degree polynomial. How many zeros were there? There were 2 zeros. Are you listening? Forming the connection? Okay. What's significant about the degree of a polynomial? It will tell you the number of zeros. Now, well, we'll get to this a little bit later on. But that is true. The number of zeros of a polynomial is equal to the degree of the polynomial. So later on, today, we're going to be looking at 4th degrees, maybe 5th degree polynomials. So how many zeros are we supposed to find then? 4 or 5, however many the degree is. Okay. Let's try another one. Maybe a slightly harder one to factor. This is just helping you practice your factoring techniques. It's pretty important to know how to factor in this chapter. And not just factor, but factor quickly. If you are taking forever to figure out how to factor, the rest of the problem is going to take you even longer. So how do we start this one? Set it equal to 0. Okay, good. So we times 2 by that negative 6. We can't factor this the exact same way as the last one because it has this leading coefficient. By the way, how many zeros are we supposed to find here? We've got to find 2 zeros because it's a second degree polynomial. All right then, 2 times negative 6, that makes a negative 12. We need 2 factors of negative 12 that add to negative 1. Exactly, negative 4 and 3. So you take this little term, or this linear term, the one in the middle, and you split it into the sum of these 2 numbers. We started with a polynomial with 3 terms. What we have now is a polynomial of 4 terms. Why in the world would we want to add an extra term in there? It is easier to factor, but why? What's the method? Grouping. It has an even number of terms now, so we can group the first 2 terms and the last 2 terms. Okay, so out of that first group, the one that's 2x squared minus 4x, you can factor out a 2x from that group, leaving an x minus 2. From the second grouping, you can factor out a 3, leaving x minus 2. Now what? This is not the first time you've seen this method, right? Yeah, because both of these have an x minus 2, you can factor out the x minus 2 as a common factor. So I'm going to factor out the x minus 2 and put it in front of a parenthesis. If the x minus 2's are gone, that's going to leave a 2x and a plus 3. So 2x and a plus 3. We're almost there. Now that we have it in factored form, it's easier to find the zeros. It's not always easy, but easier. The zeros are x equals 2. What about this one? Yeah. Negative 3 halves. It was a degree 2 polynomial, right? We found 2 zeros. Let's do part C. Okay, P of x equals x to the third minus 2x squared minus 3x. What degree do we have here? Third degree. What does that mean? There's going to be 3 zeros. What does that mean? That there's going to be 3 zeros? 3x intercepts. There's going to be 3x intercepts. Okay. How do we factor a third degree polynomial? Which is what? X. If you notice, you're right. If you notice, every term has at least one x that you can factor out. So, factor out the x. P of x equals x times x squared minus 2x minus 3. Yep. We factored out an x. That left us with a quadratic expression right here. X squared minus 2x minus 3. Yep. Set it equal to 0, and then at the same time, let's factor that quadratic expression. X squared minus 2x minus 3 factors quite nicely. Negative 3 times 1 is this negative 3. Negative 3 plus 1 is where that negative 2 comes from. Now, students generally are okay finding zeros if the factor looks like this, x minus 3x plus 1. Some students have real trouble with this one. It's 0. The way that you find zeros, and I've been skipping a step every time because I just assumed that we would be okay with it. But really what you're supposed to do after you factor it is take each factor separately and set it equal to 0. So you're supposed to say, okay, x plus 1 equals 0, x minus 3 equals 0, and here x equals 0. And then you solve all of those equations for x. This one's already solved. That's why x equals 0. Okay? On this one here, if you add 3, you get x equals 3. Here, if you subtract 1, you get x equals negative 1. Those are your 3 zeros. Okay, one more quick one. Let's not spend too much time on this because I want to get to a little visual presentation here in just a second. So part D, P of x equals x squared plus 4x plus 4. This is not just more of the same stuff. This is actually for a purpose. How many zeros do we expect to find? 2, right? Isn't that what I just said? The degree equals the number of zeros? Okay.
I think I know why this is.
What happens here?
It's a perfect square trinomial.
You're right. That's a good term. A lot of students don't remember that. Perfect square trinomial. What does that mean? What's a perfect square trinomial?
It has two terms, and each term is like if you
That's exactly what I was just going to get to. The term perfect square trinomial means the two factors are identical to each other, x plus 2 times x plus 2. That's what a perfect square trinomial is. And why is this so weird? Well, if we try to find the zeros, what do we say? X equals -2. Well, that's only one number. But it still is true. I wasn't lying to you. The number of zeros is equal to the degree of the polynomial. Okay? What this means is we're actually kind of getting into our second objective. If you look back up at the top of your notes, this second objective is called find multiplicity of zeros. Okay? Some zeros have what are called multiplicity. Even though we got one number for the zero, didn't it come from two factors? So this zero has what's called multiplicity. X equals -2, and then you say that has multiplicity. You would say that has multiplicity of 2. Why do we say it has multiplicity of 2? Because it comes from two of the same factors, x plus 2 and another x plus 2, so it has a multiplicity of 2. Now, Braden, you're already ahead of us here. You already know the significance of multiplicity, or you were saying something that has a lot to do with it. What is a zero? It's an x-intercept, right? When you guys think of x-intercepts, don't you usually think of the graph crossing through the x-axis at that point, right? But not all x-intercepts act that way. What were you just telling me, Braden?
And then if you graph it out, the parabola would tangent to the x-axis.
You're right. Let's look at this another way. Couldn't we say that 0 is equal to x plus 2 squared? Couldn't we write it that way? Writing it this way might help you remember our very last test. If there's a transformation inside of the function, what direction does it move the graph? Remember this? This was only like a week ago. It moves it to the left. Is there anything out here that moves it up or down? So if we were to graph this quadratic function, the parabola would move to the left 2 units, but it wouldn't move up or down, so the vertex is right on the x-axis. And it looks something like this. So the x-intercept, the graph doesn't necessarily cross through the x-axis at that point. It touches the x-axis. Okay? And that has to do with its multiplicity. Now I want to show you something. You can stop right, put the pencils down. Look up here for just a sec. There we go. If you can, I know it's kind of small, but look down at the bottom here, the input. I'm going to type in a function p of x, maybe. There it is. P of x is equal to parenthesis x minus 2 times parenthesis x plus 4. Now before I hit graph, let's make a prediction on what this graph's going to look like. It's x minus 2 times x plus 4. If we were to multiply that together, what type of function is that going to be? It's quadratic. So this is going to be a parabola, yes? Where is it going to cross through the x-axis? At positive 2 and negative 4. So let's see if we're right. We were right? Okay. Now, the graph crosses through the x-axis at those 2 points. Why doesn't it touch and just bounce off the x-axis? What's the significance? It has to do with multiplicity. Do any of those factors or those zeros have multiplicity? No. Are they repeated factors? No. If they have a multiplicity of just 1, what's the behavior of the x-intercept? It'll go through it. It goes straight through it. Okay? What if I added another x minus 2 factor? So it was x minus 2 times x minus 2, then times x plus 4. Then what kind of polynomial is it? It's a third degree. Okay? But one of the zeros would have multiplicity. So let me see if I can change this. I think I can. Yep. So if I multiply it by another x minus 2. Oh. All right, I screwed that one up. Let's do x minus 2 to the second power. What was the other one? X plus 4, yeah. X plus 4. There we go. Now I got to zoom out on that. So this is the graph of a third degree polynomial. But consider the zeros. This 0 right here is negative 4. Why does the graph cross through with the axis at negative 4? What's the multiplicity? 1. Just multiplicity 1. But this factor right here, x minus 2, appears twice. That means the 0 has multiplicity of 2. So what's the behavior of the x-intercept? It touches. Okay? Now, let's get a little more crazy with this. What if I did this? Now, before I hit enter, you kind of have to understand how you have to input some things here. This little upward arrow means it's going to be an exponent. So I'm putting an exponent of 3 on that x plus 4. So that means there's going to be 3 of those x plus 4s.
How is that going to work?
What degree are we going to have? If we were to multiply all this out, you'd have x minus 2 times x minus 2 times x plus 4, x plus 4, x plus 4. If you were to multiply that all together, what kind of polynomial is that?
5 degree.
That's a 5th degree? How many zeros do we expect?
5.
There should be 5, but there's a lot of repeated zeros, right?
Yes.
What's the behavior of the graph going to be? Well, what happened here? Everybody look up here. Some of you guys are not paying well enough attention back in the back. Okay? Everybody look up here. This 0 represents the number x equals negative 4. That comes from this factor. How many times is it repeated? It's repeated 3 times. Okay? What's the behavior of the graph at that x-intercept? But doesn't it still cross through? Okay. What's the behavior of this x-intercept? It bounces off. We need to start to come up with a reason why. When do the x-intercepts cross through it, and when do they bounce off of it? So we have an idea of when it's negative or positive.
When it's a multiplicity of an odd number, it crosses through. When it's a multiplicity of an even number, it bounces off.
Okay. What do you guys think?
That sounds
Because when you have a negative number to an odd exponent, it can still be negative. But if you have, it could be negative or positive, even number to an odd exponent. But if you have a number, you can be an exponent.
Okay. All of these explanations are actually pretty good, and all of them have some validity to them. What does it mean to square something? You multiply it by itself. So this 0 that comes from this factor right here, when it's above the x-axis, doesn't that mean positive y values? Okay. Why does it bounce off and continue to have positive y values? Well, if you square something, isn't it always going to remain positive? Okay. And that's what you were talking about. Now this one right here, you can't really see it, but the exponent is 3. If you take a negative number and raise it to the 3rd power, can it end up negative? That's why here the values are positive, but once it crosses the x-axis, now you can have negative values, because that's a 3rd degree. So you're absolutely right. And what you guys are saying is absolutely true as well. You have to consider the multiplicity of the 0. This is what you need to start writing down. Okay? And this is what you need to remember. Let's get back to notes. If multiplicity is even, and it doesn't matter how high, it could be multiplicity of 2 or multiplicity of 4 or multiplicity of 20. If the multiplicity is even, then the graph bounces off the x-axis at the 0. So if the multiplicity is even, it bounces off the x-axis. Why is that? If you take any number and raise it to an even exponent, it's going to remain positive. So it has to be above the y-axis. If the multiplicity is odd, then the graph crosses through. The x-axis. At the 0. So you always need to remember x-intercepts have two different behaviors. They either cross through the x-axis or they bounce off the x-axis. What determines that? The multiplicity, whether it's even or odd. Okay? Finding the zeros is important. And going back to this idea, how many zeros are you supposed to find? It's equal to the degree of the polynomial. And even if you have 2 zeros and it's a 5th degree polynomial, if you add up all the multiplicities of the zeros, then it will add up to the degree of the polynomial. That's really what's happening. So our objectives, we've done objective 1, finding zeros. How are we doing on multiplicity and how it affects the graph? Do we understand that well enough? How do we know the multiplicity, by the way? How do we know if a zero is going to have multiplicity? Whether the factor that the zero comes from appears more than once, right? So that's if it has multiplicity. Let's talk about what's called the end behavior of polynomials. Matter of fact, let's go back to GeoGebra. So, end behavior. If I typed in P of x equals x squared, you guys know what that's going to look like. Okay. It's a parabola. End behavior talks about where the graph is heading, both sides of the graph. What direction are both sides of the graph heading to? Positive infinity. Why is that? Consider the exponent. If I change the exponent to 3, to an odd exponent, always keep in mind the idea of even versus odd. If I change this to x to the third, does anybody remember what an x to the third graph looks like? So what's the end behavior now? One side is still going up to positive infinity, but the other side is going to negative infinity. What's the only thing that changed in the equation? The exponent. What if I changed it back to an even exponent now? What if we went back to a 4th degree? You probably haven't ever seen a 4th degree graph. What does it really resemble? What does this graph resemble? Doesn't it resemble a parabola? It's kind of hard to tell the difference. When you look down at the bottom, do you see some kind of a difference down here at the bottom? It's a little more flat. But the key we're trying to see here is the end behavior. What's the end behavior of this? It's the same end behavior as x squared, isn't it? Okay.
It looks like that looks like x to the third, and the bottom, the one that was going down, flipped up.
And why is it? Why is it flipped up? Anything raised to an even exponent has to be positive. That's why both sides are heading into the positive direction. Hopefully you guys are seeing a pattern now. Before I even hit graph, tell me what's going to happen if I change this to a 5th degree polynomial. What's going to happen to the end behavior? It's going to go back to the end behavior of x to the third. What's really the only difference here? Look near the origin. Just a little more flat. But the difference, the key here is the end behavior. One's traveling up. The other one has negative values because you can have negative values with an odd exponent. Okay? So on your notes, let's just jot down a few of these, just a rough sketch. Y equals x squared. Draw a quick graph. Oh man. Not like that. Let's try that again. There's a very particular way that you need to describe end behavior. Ooh, that's better. Okay. Watch carefully. Do this exactly how I do this. There's a very particular way that has to be done. End behavior has two sides because there's two sides to a graph. There's the one going up to the right and the one going up to the left. So you have to have two parts as you describe end behavior. So let's first describe this one. As x approaches infinity, there's another part of this, and we got to figure out how to write it. So as the x values get larger and larger, 2, 3, 4, 5, what's happening to the y values? What are they approaching? This arrow means approaching. As x is approaching infinity, what's y approaching? Infinity. So that's the end behavior on the right side of the graph. You have to state it this way. As x approaches infinity, y approaches infinity. And then on the other side of the graph, we have to state it similarly, but this time what is x approaching on the other side? So we would say, as x approaches negative infinity, y approaches positive infinity. Critical thinking question for you here. Y equals x squared. Let me ask you this. Any quadratic function, it doesn't have to be just plain x squared. We can start putting numbers here, linear terms and constants. Any quadratic function is going to have that exact same end behavior. True or false?
True.
What do we think? Any quadratic function. The vertex doesn't have to be a 0, 0. Any quadratic function is going to have that same exact end behavior.
No, because they're upside down.
What if it is facing upside down? Then what's the end behavior? Then we would have to say y goes to negative infinity. But the key here is, aren't both sides of the graph at least heading in the same direction? Whether it's positive infinity or negative infinity, aren't both sides of the graph going to the same place?
Yes.
Why is that? The exponent is even. Okay? Now, let's compare that to an odd exponent. And again, it doesn't need to be exact, just make kind of a quick sketch of a third degree graph. The way you would state this end behavior is exactly the same way that you state this one. As x approaches infinity on the right side, as x approaches infinity, what's y approaching? Y approaches positive infinity. But on the other side, as x approaches negative infinity, y approaches negative infinity. The key to remember here, both sides of the graph are not traveling to the same spot. One's going up to positive infinity, the other side is going to negative infinity. Why is that? The exponent is odd. And these are really the only two you need to remember. Because every other graph that I had on that GeoGebra part, didn't every other graph essentially look like one of these two? Okay. This is what's called end behavior. All you need to remember is if it's an even exponent, if the highest degree is an even exponent, it has that end behavior, like y equals x squared. If it's an odd degree polynomial, it's going to have that end behavior. Okay? And that plays a key role in helping us graph. If you can remember end behavior, these graphs become a lot easier. So, that is objective 3. Any questions on end behavior of polynomials? What determines end behavior? The degree. The degree of the polynomial determines end behavior. Okay? What do you have to differentiate between? Whether it's even or odd. Even or odd. That determines the end behavior of polynomials. Let's get to the most important part of the lesson. Graphing. You ready for this? Graphing polynomial. Graphing polynomial functions. It can become very procedural, meaning it's just a list of steps or an algorithm. It's not something that you have to guess at every time and it's different every time. It's not different every time. There's a procedure. If you can remember and follow this procedure or list of steps, this really isn't that bad. The problem is you have to remember this list of steps. Okay? Step 1 is to write the polynomial in factored form. Why? Why would we want to write it in factored form? So you can see the zeros. That's step 2. Very good. Step 2 is to find. If it's not in factored form, you're not going to find the zeros. Find the zeros, and this is critical. Find the zeros and their multiplicity. You don't just find the zeros. You have to find the multiplicity, because that determines the type of zero it is. Is it one that crosses through the x-axis, or is it one that bounces off the x-axis? So find zeros and their multiplicity. Step 3, this is kind of an easy one. Find the y-intercept. Step 4, determine end behavior. And finally, once you've done all of that, you can sketch the graph. Now, I didn't really talk about step 3, but it's really kind of an easy thing to do, because you find the y-intercept the same regardless of the type of polynomial. It can be, or the type of graph for that matter. It could be an absolute value graph, a quadratic, it can be any type of graph. You find the y-intercept the exact same way every single time. Let x equal 0. That's how you find y-intercepts of any graph, of any sort of graph. So let's try it. What are we on, example 11 or 12 or 19 or 48? Only on example 2? What? Whoa. I've been talking for like 40 minutes. We're on example 2? Holy smokes. All right, then. Sketch the graph. We're just about done with 3.2. I'll give you guys like a 2-minute stand-up break and walk around, but we have to start 3.3. We got to get it going today. We may not finish 3.3, but we got to get going on it at least. We're a little behind schedule. So the polynomial is p of x equals x to the third minus 2x squared minus 4x plus 8. Right off the bat, how many zeros do we expect to find? 3. Now, here's a question. Are they all going to be distinct zeros? Are we going to find maybe 3 distinct zeros? Maybe. We could. What's more likely to happen is one of the zeros may have multiplicity. So just keep that in mind. Holy moly, how do we factor this? Could we take out an x? Not everything has an x, or an x squared for that matter. How many terms does it have? 4. It has 4 terms. So we ought to try at least factor by grouping. Now, just because something has 4 terms doesn't mean it factors by grouping. If we get lucky, this may factor by grouping. From the first grouping, we can factor out an x squared. And that leaves x minus 2. All right, be really careful with this next grouping. If that first number of the second grouping is negative, you must factor out that negative with the number. So what are we factoring out? Factoring out the negative 4, which changes the parenthesis into an x minus 2. Why did it change to x minus 2? Because a negative 4 factored out of a positive 8 makes a negative 2. Factor out means divide. Okay, so now if we continue to factor by grouping, we're going to have x minus 2 times x squared minus 4. That's kind of helpful, as long as you remember your difference of squares. It's easy to forget, but does this look familiar to anybody? X squared minus 4. The difference of squares. It factors kind of nicely. What does x squared minus 4 factor into? X plus 2 and x minus 2. Oh, I should have mentioned this. By the way, let me go back a step, sorry. This first step right here, write the polynomial in factored form. Why isn't this right here? Why didn't we stop right here and say, okay, that's factored form? Why didn't we stop there? Why is it not fully factored? You're right, but why? It has to do with what's inside. To be fully factored, the highest exponent inside a factor has to be 1. Or you can think about it this way. If it's a third degree polynomial, there has to be 3 factors. They don't have to be distinct factors, but there has to be 3 factors. That's when you know it's fully factored. And I'm going to write this one more change. I'm going to write it this way. X minus 2 squared times x plus 2. That was all step 1, right, in factored form. Let's state the zeros and the multiplicity. Zeros and their multiplicity. What are the zeros or the x-intercepts? X equals negative 2. This one doesn't have multiplicity, so I'm not going to state anything there. But x equals positive 2 with multiplicity of 2. Now, I always do this just to help me remember. You don't necessarily have to do it this way, but it may help you remember. What's the behavior then of that particular x-intercept? If it has a multiplicity of 2, am I going to write the word crosses or bounces in this parenthesis? Bounces. What about this one here? Am I going to write the word crosses or bounces? This one crosses through because it doesn't have a multiplicity that's even. It has a multiplicity that's odd. Okay, there's step 2, finding the zeros. Look back at your notes. What's step 3? Find the y-intercept. We just found x-intercepts, so it makes sense to find the y-intercept. Question for you. Think carefully before you answer. Could there be more than one y-intercept?
No.
Think carefully about answering that.
No.
The answer is no. Why is that, though? Wouldn't be a function. If you had a y-intercept here and then a y-intercept here, that wouldn't pass a vertical line test. So it wouldn't be a function. So there is only one y-intercept. You let x equal 0. Now, just to give you a little hint, it's much easier to find the y-intercept in general form, which was what we started with here. Much easier to find the y-intercept in general form. Because if you let every single x equal 0 and it's in general form, all the terms that have x's go away, leaving what? The constant. Okay? Which is 8. If you want to do it in factored form, that's fine. You just got to have to do a little bit of arithmetic. 0 minus 2 is negative 2. Negative 2 squared is 4. And then here 0 plus 2 is 2. 4 times 2 is 8. So you get the same number. It's just much easier to find it in the general form. But any way you do it, it's going to be the same thing. The y-intercept is the point 0, 8. Now let's consider the degree, or the end behavior. Determine end behavior is step 4. What's the degree? Degree 3. Now I'm just going to put this in a parenthesis. This may not be exactly what it looks like, but because it's degree 3, isn't the basic shape of the graph going to be something like this? Because it's degree 3. So we just got to make sure that our graph looks something like that. Okay. Really what we're looking at here is the end behavior. The end behavior, one travels to the right, up to the right, one travels down to the left. Let's sketch the graph now. We got everything we need. Sketch the graph. First, plot your x-intercepts. We had one at negative 2, one at positive 2. Next, plot your y-intercept. Now, just try to listen carefully to what I do here and try to keep an open mind about it. This step right here, degree 3, and then looking at the end behavior, really only helps you to know that after it deals with this x-intercept, then that part of the graph is traveling up. This part of the graph is traveling down. What we have to figure out is how does the graph behave in between these two end behaviors. Does that make sense? Okay. We've got to figure out how am I eventually going to be able to connect these points, or connect these two ends of the graph. Okay. So, as the graph is traveling from left to right, so I'm starting here, what happens to the graph as it reaches that x-intercept? Is that the one where it crosses through, or does it bounce off of it? Okay, so we cross through the x-axis. Now we're up above. Where does it go from here? We know it's eventually going to reach the y-intercept, but you guys listen carefully to this because I do have to mark points off for inaccuracy. How do we know it goes right to the y-intercept? What if it goes like this? How do we know if it's going to do that or not? You know what I mean? So what can we do between negative 2 and 0 to find out where the graph is? We have to plot points. We have to figure out where the graph is at negative 1 to determine the true behavior of the graph before it reaches that y-intercept. So if you make a little xy table here and just plot a point of negative 1, you can either put it into the factored form or the general form. I'm actually going to put it into the factored form. If you put a negative 1 in for that x and a negative 1 in for that x, and then do the arithmetic, what's negative 1 minus 2? Negative 3 squared is 9. Negative 1 plus 2 is 1. 9 times 1 is 9. So that graph actually goes above the y-intercept and then comes back down through it. So at negative 1, we're all the way up at positive 9. Which is about right there. So the graph goes up to positive 9, then it crosses through the y-intercept. Now what happens between 0 here and positive 2? We've got to plot another point of 1. So now let your x's equal 1. 1 minus 2 is negative 1, but negative 1 squared is 1. 1 plus 2 is 3. 1 times 3 is 3. So at x equals 1, you're at 3. So the graph crosses through the point 1, 3, and then it heads towards that x-intercept. What's the behavior of that x-intercept? It bounces, so it's just going to touch the x-axis and bounce off and connect with that part of the end behavior. That's what the graph looks like, or a rough sketch. If we wanted to get an exact sketch, we'd have to use technology in our graphing calculator. But We don't. We're limited to do this by hand. Answer this question, please, quick. Didn't I just, at the beginning of the lesson, what's the domain of any polynomial? All real numbers. What about this one? This one's also all real numbers. Okay, let's do example 3. Example 3. Okay. X plus 2 squared times x minus 1 squared. They will sometimes be given to you in this form, and that's actually kind of a nice thing. What's the nice thing about giving it to it like this? Already factored. We don't have to go through the process of factoring. It's already been factored for us, which is awesome. So we go right into stating the zeros and their multiplicity, which are x equals negative 2 with multiplicity with a multiplicity of 2. And I always just like to make a note of what that means. That means the x-intercept bounces there. The other zero is x equals 1 with multiplicity of 2. Also bounces through the x-axis. Ready to think critically for just a second? Is there any piece of this graph that will be below the y or below the x-axis?
No.
How come?
Because there's no even exponent.
No matter what you choose for x, you're going to eventually be squaring it, which is always going to result in positive numbers. Every piece of this graph is going to be above the x-axis because it has to result in positive numbers. So there's the zeros. Let's do the y-intercept. You always let x equal 0 for this, for any type of graph, not just polynomial graph. Unfortunately, we don't have the general form, we just have the factored form, so you got to do the arithmetic. 0 plus 2 is 2 squared is 4. 0 minus 1 is negative 1 squared is 1. 4 times 1 is 4. So the x-intercept is 0, or the y-intercept rather is 0, 4. This one sometimes is a little bit harder for students to see, especially when it's given in factored form already. But what is the degree of that polynomial? It would be degree 4. Because if you were to multiply all of those factors together, there's 4 factors, which would result in some kind of an x to the 4th term. So it is degree 4. So just a rough sketch to determine end behavior. If it's degree 4, what's the end behavior? They're both going in the same direction. It's a lot like an x squared graph. It's just maybe a little bit flatter down towards the bottom. So the end behavior at least has to look like this. What's happening in the middle, you know, may not look like this, but the important thing is the end behavior is about the same. So sketch the graph. Say what?
It said it goes all the way up, so like for x equals 2 equals y equals 16.
Ooh.
Kind of hard to balance.
Yeah. Let's do the zeros first. We have 1 at -2. And we have 1 at +1. And we know the y-intercept is 4. We also know the end behaviors need to look like this. One's going up, and the other one's going up. That's the end behavior. What we've got to figure out is how to connect the two pieces of the graph. So let's go from left to right. So we're traveling from left to right. The graph comes down to this 0. What happens there? Now, I need you to pay attention to this. If you draw your graph like this, I'll have to mark a point, maybe a half a point off. Why? It's not smooth. Yeah, it's not smooth. Polynomial graphs are smooth. You can't have any corners. So I know it seems ticky-tacky, but you got to be careful on how you graph that. So just make sure it's a rounded edge when it bounces. Okay. Now, does it go straight to the y-intercept? We don't know. It may, but we don't know that. We have to plot the point -1. Plot the point -1. -1 plus 2 is 1. 1 squared is 1. -1 minus 1. Well, this is odd. -1 minus 1 is -2. -2 squared is... So we have the point -1. Does that strike anybody else as odd? So we have -1 comma 4. How does that work? We didn't do anything wrong, and that is right. Does it do this and then go straight over? What's more like that? That's actually not what happens. What's more likely to happen? Goes a little bit more above that, and then it comes down. Now, listen carefully. To know exactly how high that graph goes, we actually have to know calculus. That's something that you're going to learn next year in your calculus class. So for right now, with what we know, we're just going to have to go up a little bit more and then come back down. Exactly how high it goes, we're not going to know, and that's fine. Okay? It does now cross through the y-axis, and it comes down to this 0. What happens there? Bounces and connects up with that one. Let's do domain. This one should take you half a second to answer. That was too long. All real numbers. Did I ever show you this symbol? Or have you seen this symbol before? That means all real numbers. Kind of. Range? This one's not all real numbers. What's the range? Including 0. So it's 0 to infinity, yeah. All right, that's it. That is 3.2. Holy smokes. Stand up.